Okay, so let me just recall where we were last time. Okay, so we had seen convergence of sequences. So we had defined what it means for a sequence to converge to a real number. And then we had developed two kind of useful criterion for when a sequence converges. Okay, so the first one was that if I had another sequence which converged to 0, which consisted of positive numbers, and I had that the terms of my sequence, xn minus x, were less than or equal to CAN, for say all n bigger than or equal to some fixed number, this implies that the sequence xn converged to x. Okay, so if we wanted to show that something converged to x, you could compare it to a sequence which converged to 0. Okay, and the other one, which we saw at the end, was that if we had a convergent sequence, then the absolute value of xn is less than or equal to some k for all n and n. So our sequence was bounded. All right, so this gave kind of the first criterion for non-convergence of a sequence. If you saw some sequence where the terms are going off to infinity, then, or getting arbitrarily large, then the sequence can't converge to something. So today, we're going to essentially, develop some tools to show convergence of sequences, which are a little more complicated than what we've seen before. Okay, so what we're going to see is interactions between convergence and are the operations that we've been given. So plus, minus, times, etc. Okay? So let me and essentially everything behaves as you might expect. So if xn and yn are sequences, maybe I'll add, and zn is a non-zero sequence. So that, zn is not equal to 0 for all n. Then we can form a lot of new sequences by applying our operations. So I can say the sequence xn plus yn, okay, this is going to be defined as just the sequence where you add the terms. Okay, so over here I have kind of a new sequence, and this is how it's defined. Similarly, I can say xn minus yn is just the sequence where you subtract the terms, xn times yn. Maybe I'll do one more since I included this z, so xn divided by zn, xn divided by zn is defined to just be xn over zn. This is where I had to assume that zn was not equal to 0. I could say c times xn is defined to be cxn. And you can imagine there's just, too many possibilities to write them all down. Okay? So anytime you can essentially do any operation of real numbers, you can extend that to an operation on sequences just by doing the operation on each component of the sequence. Okay? And now you want to know what happens with convergence. Okay, so basically everything happens as you would expect. So here's a basic result. So if xn converges to x, and yn converges to y, zn converges to z not 0, I have to again assume this is non-zero. And also I need the limit to not be 0, okay? Then, well, xn plus yn goes to x plus y, xn times yn goes to x times y, cxn for c in the real numbers goes to cx, xn over zn goes to x over z. Everything you might hope for is true, okay? So the one thing you have to be a little careful of is when you're dividing and then you have something which goes to 0, that can get you screwed up, but we'll see examples of that soon. So I'm not going to prove, I'm going to leave some of these, or one of these maybe as a lecture problem. So this will become a lecture problem. Let me prove the product one, which is slightly trickier. And then once you have these, you can, if you have addition and multiplication, it's pretty easy to get something for division, something for subtraction, so I won't prove those. Okay, so here is our goal. Well, we want to show something about the terms xn, yn minus xy, but we only know something about xn minus x and yn minus y, okay, when n is very large. So we know that both of these terms are small, and what you want to know is that the product is small, okay? So this is going to be kind of similar to the algebraic manipulation that we did, I think in the last lecture, where we added a 0 to something in a clever way, and used the triangle inequality to put it inside of terms that we understand, okay? So this is kind of a jazzed up version of this. So notice that xn yn minus xy is also xn yn minus xny plus xny minus xy. Okay? And we're putting this in because what we see here is an xn times yn minus y, and we know something about yn minus y. And we're putting in an xn minus x, and we know something about xn minus x. Okay? So now this is less than or equal to xn yn minus xny. So this is by triangle inequality, plus xny minus xy. And this is less than or equal to the absolute value of xn. So I have to take out the absolute value because xn might be negative, okay? Times yn minus y plus xn minus x times y. Okay, so now let's look at each of these terms, okay? Well, we know that this one is going to be approaching 0, okay? Because yn converges to y. Similarly, we know xn goes to x, so we know this is going to 0. We know this is just some, bounded. That's all we care about at this point, okay? So it's some number in the real line, and it's fixed, right? It's just, the number y. This one is changing, right? We have xn, which is a sequence. What you might worry about is that this is going to 0, but this is going off to infinity. And then maybe this limit, or this product, isn't getting small. On the other hand, this is bounded, so xn approaches x. So for sufficiently large n, this term, so xn, is less than or equal to, say, x plus 1. Okay? It might be, again, you have to be a little careful because these things might be negative, but like x might be negative, and you have to be careful. If I wrote less than or equal to x plus 1, that would be a little fishy, okay? But the absolute value is okay, and that's what we care about. So now, what this means is that we can take m to be the max of y and x plus 1, and then for large n, okay, so in other words, there exists some n in R, so that for all n greater than or equal to this, we have that xn, yn, minus xy is less than or equal to m times y minus yn plus x, that's minus x minus xn. Okay? We don't know what m is, but this is okay. We know that it's a fixed number, okay, for sufficiently large n. And now we just let epsilon greater than 0 and choose n in R so that y minus yn is less than epsilon over 2m, and x minus xn is less than epsilon over 2m for n bigger than or equal to n. Okay? So again, since these two sequences converge, you can do this, and then they might converge at different rates, but you just take the larger value of n that you get from each sequence. Okay, so this is some max of a value for x and a value for y. And now we've cooked it up so that xn yn minus xy is less than or equal to m times, actually strictly less than epsilon over 2m plus epsilon over 2m, which is less than epsilon. Okay? And that, therefore, xn yn converges to xy. Okay, so that's essentially how, I would encourage you to, check the division argument, and as I said, the sum of two sequences will be a lecture problem. It's always kind of a similar type of game. It's just figuring out what the right constants and the right bounds should be. Okay? So now what I'd like to do is start giving different criterion for convergence of sequences. Okay, so let me emphasize this. So far, we've always had to rely on previous knowledge of convergence or somehow guess the limit in order to prove convergence. Okay, so this is, you can go back and check all the examples that we've done, right? Essentially everything that we've proved, on how to make sure that a sequence converges to something, was all reliant on the fact that the sequence 1 over n converged to 0. And then every other thing was doing some, clever algebraic manipulation so that we could compare our sequences to the sequence 1 over n. And if we had something like 3n plus 6 over n minus 2, the only, to compare it to 1 over n relied on us having to guess that the limit was 3, right? So we had to know that somehow the right thing to do was to set up this, this difference and try to compare it to 1 over n. But if you didn't know what the limit was at all, how would you know to put 3 there? Okay, so what we'd like is somehow a way to get convergence of sequence without having to guess the limit. And in general, there's no way to do that, unfortunately. But sometimes we have ways around this, okay? There are ways around this. Okay, so let me give you a couple definitions, and then I'll give you the main theorem for today. Okay, so here is a definition. So we say the sequence xn is increasing if x1 is less than or equal to x2, less than or equal to x3, and so on. Okay? Decreasing is just exactly x1 greater than or equal to x2, and so on. Okay? So I'm assuming that they can be equal. Sometimes you can say a sequence is strictly increasing or strictly decreasing if you want strict inequalities rather than less than or equal to or greater than or equal to, but this won't really come up too much for us. So we say x is monotone if it is either increasing or decreasing. Okay? So let me give you some examples. I mean, essentially the picture, of course, is that you can have a sequence which looked like this. And I know I'm drawing a graph, okay, but really this is motivated by looking at increasing or decreasing functions. So the picture looks something like this, okay? And these would be the terms of my sequence are in an increasing function, and this would be my terms in my sequence of a decreasing function. And I know I included the domain of negative numbers here, but I hope it's still good motivation. Okay, so let me give you an example. Well, we've seen some of them before, right? 1, 1/2, 1/3, 1/4 is a monotone function. It's strictly decreasing, okay? There is a function or a sequence which looks like this, which just goes from 1, -1, 1, -1. This is not, right? So this is not monotone, and this is. All right, so here is the main theorem for today, which is called the monotone convergence theorem. And it says a bounded, so you have to assume, if you want to get something about convergence, you have to assume bounded. And of course, this sequence, 1, 2, 3, and so on, is a monotone function, which does not converge. So a bounded monotone sequence is convergent. Okay? And moreover, you know what the limits are, though it might be tricky in practice to work them out. So if it's increasing, then the xn's converge to the sup of the set xn. And if it's decreasing, then the xn's converge to the infimum of the set. Okay, so let me prove this. Let me first draw a picture for what this should look like. So we have the real line. We have our sequence. I'll do the increasing case. It's kind of exactly the same proof for the decreasing case. So we have a sequence which is monotone and increasing, and we also know it's bounded. So up here, we know that there's some m in R so that every xn is less than or equal to m, okay? For all n and n. So what this means is that somehow the x3 are trapped. They can't go off to infinity. They have to converge, or at least stay in this interval. And then what the theorem is saying is that they have to end up converging to the supremum of the xn's. Okay? So what we know, what the real numbers give us, is we know that the supremum exists. Okay? So let me just label this. I'm going to call this y, which is the supremum of the set xn for n and n. This is a real number by completeness. Okay? And now what do we have to show? Well, we have to show for any epsilon greater than 0, we have to find this n, which bounds the distance between y and the xn's for sufficiently large n. Okay? So what do we know about this? Well, we've already seen that when we worked with supremums, so here's the supremum in my picture y, we know that we can find elements of the set xn, or the sequence xn, which are arbitrarily close to our supremum. Okay? So in particular, y minus epsilon is not an upper bound of the set xn, so there exists an n in n so that xn is greater than y minus epsilon. Okay, otherwise y minus epsilon would be a smaller upper bound than y, but y is the supremum. Okay? So what this means is that actually we have y minus epsilon less than xn, which is less than or equal to y. And now, well, what are we going to do for all n bigger than this n? So for all n bigger than n, since the sequence is monotone, or monotone, I'll say monotone, though in this case we're saying increasing, but this would just be the same proof for decreasing sequences. What you would have is that for any n bigger than or equal to n, we have xn, which is less than or equal, I'll put this here, y minus epsilon, less than xn, less than or equal to xn, which is less than or equal to y. Okay? And therefore, in particular, we get that xn minus y is less than epsilon for all n bigger than or equal to n. Okay, so that's the proof. It converges. Okay, so notice this is like, it's a very special case, but it's an important case. Okay, so we will see, let's see some kind of applications of it. Maybe I kind of want to introduce this new notation, which I'll kind of go between using the two of them. So when I write the limit n goes to infinity of xn is equal to x, this is exactly the same thing as the sequence converging to x. Okay? Sometimes it's just going to be convenient to use this notation. Okay, so let me do an example which shows you kind of the power of the monotone convergence theorem, which is that the limit as n goes to infinity of 1 over the square root of n is equal to 0. Okay? So notice we can't use immediately that the 1 over n goes to 0. Okay? Because 1 over square root of n is, so 1 over square root of n is not less than or equal to c over n for any c. Okay, so this is a new kind of sequence that we can handle once we know monotone convergence theorem. Okay, so first let's check that we can apply it. Well, it turns out we can. This is bounded. It's easy to check. It's also easy to check that it's decreasing. And so therefore you know it converges. And somehow this is powerful, right? We know that it converges without doing anything. And now we can work out what it kind of has to converge to, okay? So I'm just going to call this x for now. So that's what it converges to. So we know the limit as n goes to infinity of 1 over square root of n is equal to x. Well, this implies that the limit of n goes to infinity of 1 over n, so maybe I'll write this, 1 over square root of n times 1 over square root of n goes to x cross x, right? Because we know that the limit of two convergent sequences converges, the product of two converges to the product of the limits. But we know what this is. This is the limit as you go to infinity of 1 over n, so this is 0. So therefore we get that this limit, which we kind of never really computed, happens to square to 0. So therefore x is equal to 0. Okay? So now let me do another example. Let me just say the idea here is we're going to use knowledge of convergence to show that a certain limit of a sequence has to satisfy some algebraic relation. Okay? So you'll see in the example how this is coming up. So let's suppose I give you a sequence x1 is 2, x2 is square root of 2, x cubed is square root of 2, x to the fourth is square root of square root of square root of 2, and so on. Okay? So this is a perfectly good sequence, which I can define inductively, right? So xn plus 1 is just defined to be the square root of xn. And now I want to say what this limit has to be, okay? So first, if we want to apply monotone convergence theorem, we should check that this is monotone, or actually check that it's decreasing. Okay, so this isn't too hard to show. Well, everything is bound. Oh, I should also check bounded, sorry. So notice that since we're taking a square root of a positive number, we're always going to get a positive number. So it's bounded below by 0. And it's also bounded above by 2. So when you take the square root of x and x is greater than 1, this implies that the square root of x is less than x. Okay, and also greater than 1. So if you do this inductively, you're starting at 2, then you're taking the square root, which is smaller but still strictly greater than 1. Taking the square root, you're still smaller, strictly greater than 1, and so on. Okay, so you turn out to be bounded above by 2, and really what I've told you is that this is a decreasing sequence, okay? Because every number is getting smaller, but still bounded below by 1, and therefore the square root continues to make it smaller. Okay, so therefore, we know that this sequence converges. That the xn's converge to x. Okay, but notice that we also know that the sequence xn plus 1 converges to x. Right? They have to have the same limit because the limit only depends on the tail of the sequence. Okay, so it doesn't matter what kind of the first couple of terms are. As long as you have the same kind of end behavior, you have the same limit. Okay? So therefore the limit, which I'll call L, the limit of the xn's is equal to the limit of the xn plus 1's. But on the other hand, what we've defined is that xn plus 1 is the square root of the xn's. So therefore, the limit of the xn is the same as the limit of its square root. So what does this mean? Well, this is the square root of the limit of the xn's. So therefore, this limit, which I'm calling L, so I have that L is equal to square root of L. Okay? Which means that L is equal to 0 or 1, but the xn's are greater than 1 for all n. So the limit can't be 0, so the limit has to be 1. Okay, so this kind of behavior, or this argument, happens a lot when you're doing sequences that are defined inductively. So what usually happens is that what you end up with is some algebraic criterion which the limits have to satisfy, and it kind of comes from the algebraic criterion that the sequences satisfy. Okay, so notice that these are essentially the same expressions. And then what generally ends up happening is you use this to solve what it has to be, and then you have to work out whether the sequence, which of the answers makes sense depending on the sequence that you started with. Okay, so I think this is kind of a somewhat non-intuitive example, so let me just give you another example of similar flavor, and hopefully this procedure starts to make more sense. Okay? So let me do another one where I'm going to set x1 to be 2 and xn plus 1 to be 2 plus 1 over xn. Okay? Now to be fair, I'm not even going to check whether this satisfies the monotone convergence theorem. Let's just suppose we knew it was bounded. Okay? Or sorry, suppose we knew that the sequence xn was convergent. Okay, I'm not claiming that we can apply monotone convergence theorem here, or at least I don't want to work out the algebra to check it. But suppose we knew it converged. So then I can again do this trick where, well, maybe I'll say, sorry, L is going to be my limit of the xn's. And again, we know that this is equal to the limit of the xn plus 1's, which is just equal to the limit as n goes to infinity of 2 plus 1 over xn. Okay? And now, well, we do know, so we know this is kind of easy to figure out from these inductive formulas, that the xn has to be greater than or equal to 2 for all n, so therefore the xn's are not 0. Okay, so that's just important here. We don't want to be dividing by 0. So now we apply the same idea, and we get that L is equal to the limit of the xn plus 1's, which is the limit of 2 plus 1 over xn, which is the limit, which is 2, plus the limit of 1 over xn. So L is equal to 2 plus 1 over L. Okay? Now, we can solve for L. And you get the equation L squared minus 2L minus 1 is equal to 0, which gives you L is equal to 1 plus the square root of 2. Again, this kind of comes from nowhere. Okay, but this is, again shows kind of the power of knowing that a sequence has to converge, even if you can't immediately work out what the limit has to be. Okay, so you may be saying at this point, wait a second, before we had 0 or 1 as possibilities, here we have another solution for L. Right? L could have been 1 plus square root of 2, but L could also have been 1 minus the square root of 2. Okay, that's another solution to this equation. How do we know which one is correct? Well, in this case, you can show that it has to be this limit because the xn's are always positive. Okay, so this one has to be the correct limit. And it's very reasonable now to ask why this number comes up at all, right? What is the 1 minus square root of 2 doing here? Okay, so notice that if we had, I'll just do it this way, if x1 was equal to 1 minus square root of 2, and xn plus 1 was equal to 2 plus 1 over xn, well, let's just work this out. Let's just work out what x2 would be. So x2 would be 2 plus 1 over 1 minus square root of 2. So this is 2 times 1 minus square root of 2 plus 1 all over 1 minus square root of 2. This is 3 minus 2 square roots of 2 over 1 minus square root of 2, which happens to be 1 minus the square root of 2. Okay? So therefore, if we had started at 1 minus square root of 2, then the limit would be 1 minus square root of 2. In particular, the value would just be the sequence would just be a constant sequence. Okay, so what you end up having is you have 1 plus square root of 2, 1 minus square root of 2, and the value that you choose, okay, so I'll just put some possibilities here. So x1, 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 and this is the general picture, okay? You'll have some solutions or some real numbers which satisfy the equations that your limits have to satisfy, and then kind of the initial term in your sequence will determine which limit it goes to. Okay, so you might have, if you put in different sequences with initial terms different, some of them might converge to 1 plus square root of 2, some of them might converge to 1 minus square root of 2, and that's something that always requires more analysis. Okay. Okay, so I think that's going to be enough for today. Thanks.